Here's our essential question for this video class. How do I use transformation notation to describe a transformation? How do I use transformation notation to describe a transformation? Now there are three transformations you learned last year: translation, reflection, and rotation. And now we're adding the fourth one to our list, which is, in the fourth column, dilation. So let's go over the basics of transformation notation. What I want you to see with this is if you start off with a point, I'm going to put this in the top margin here. If you start off with a point or a coordinate on your coordinate plane and it's labeled XY, transformation notation helps us describe what's going to happen to that point as it goes through a particular transformation, either translation, reflection, rotation, or dilation. So let's just make up one. I'm going to say this: x negative y. What this is telling you is, here is the old point. The old point we're just calling x and y. And this is going to change into our new point, or our new location. So, oops, I'll just put new point. Okay, new point. So let's take a look at what happens here. X and y become x negative y. That means our x value didn't change, and our y value just flipped signs. So this is what transformation notation means. It's a way to describe a translation in a coordinate plane. So let's take a look at a couple examples of this. Okay, first one, let's say that we want to take a point or an image. Okay, it could be an image or a point, and we're going to slide it. Remember, translation can be described as sliding. We're going to slide it left 2 units and up 3 units. This transformation notation describes this. This means we're going to take our original point and look what's happening. We're going to take the x value and subtract 2. Subtracting 2 from an x value moves you to the left on the coordinate grid. And we're going to take our original y values and we're going to add 3 to them. That means we're going to move them up. So this transformation notation describes taking a point and sliding it left 2 and up 3. So let's do an example of this. Another example of this. Let's say that we had a starting point. We're going to use this transformation notation. Let's say we have a starting point that was at 6, negative 3. The transformation from that to our new point, if we want to slide left 2 and up 2, or up 3, is to take our x value now and subtract 2 from it, and take our y value, which was negative 3, and add 3 to it. Take a look here. This was our original xy, and now that xy is being changed to our new value. And so our new value is going to end up being 6 minus 2, which is 4. Negative 3 plus 3 is 0. So by using transformation notation, we were able to describe sliding a point left 2 and up 1. Here's our new point. This new point compared to our old point is 2 units to the left and 3 units up. Here's another one. Let's say that we want to slide our shape or our coordinate just down 1. Take a look at our transformation notation. Our x value is not going to change because we're not moving it left or right. Our y value is going to change because we're going to make it go down 1 unit. So here's our example of that. Let's say we took a point, same point, 6, negative 3. And now we're going to go ahead and transform that. X stayed the same, but our y value, we subtracted 1 from that. So our new point is going to be at 6, negative 4. So there's the basics for transformation notation as it relates to translation. Let's do reflection. So reflection, let's just pretend we're going to reflect something by flipping it across. Let's use the x-axis. Well, here's what happens when you flip a shape across the x-axis or a coordinate across the x-axis. The x value doesn't change, but the y value flips a sign. So here's an example of that. Let's say we picked the coordinate 4, 3, and we're going to transform that by reflecting it across the x-axis. The x value doesn't change. The y value flips sign. Remember again that this is our original xy value, and this is our transformed value, which if you plotted this on a grid, you'd see all it did was it reflected to the left of the x-axis instead of to the right. And actually, let me just look at this real quick to verify this is correct. Our y value changed. Yes, so it flipped from the top of the x-axis to the bottom of the x-axis. That's a flip across the x-axis. Okay, let's do another example here. How about if we want to flip across the y-axis? There's the only two reflections you need to know in this unit. Flip across the y-axis. When you flip across the y-axis, the x value flips sign, the y value stays the same. So here's an example of that. If I start off with 4, 3, if I run it through my translation, the x value flips sign and my y value stays the same. If you graph this, you would actually see the point 43 gets moved to the other side of the y-axis. Alright, so there's transformation notation for reflection. Here is the strangest one of all, and to practice this to get better at this, but rotation can be very confusing. Let's take a look. How about if we rotate, we're going to turn an object or a coordinate 90 degrees clockwise, and we're going to say we're going to do it around the origin. That means our rotation point is the origin. You should have learned that last year with rotation. Rotation always has a point of rotation that you're rotating around. We're going to rotate around the origin. Here's our example. We've got x, y being changed to y negative x. This describes a 90-degree clockwise rotation around the origin. Let's do an example of that and see how that looks. If I had a original point of 2, 3, then when I translate that, now here's the part that might be tricky for you. Notice that the y and the x values are getting flipped around here. So now our y value was 3. Now that shows up at the front of our new coordinate, and our x value changes to the back of our coordinate, and it flips a sign. That gets us to rotate our points. And if I'm going to write here xy became y negative x. We'll do one more example just to show the possibilities of rotation. How about if we turn 180 degrees? So now we're moving not just a 90-degree rotation, we're going to go all the way, well, halfway around the coordinate grid. So turn 180 degrees around the origin. And again, the only rotations we'll be doing in this unit will be around the origin. Here's the transformation notation that describes that. So if I have a point 2, negative 3, this transformation notation shows, again, take a look. In this case, the x position stayed the same, but the sign flipped. And the y position stayed the same, but its sign flipped. Well, it was negative 3, now it's positive 3. If you plot that on a grid, you'll see that rotated 180 degrees around the origin. Let's make a little note just to show you this again. This was x, y, and this became negative x, negative y. So there's our rotation. We'll do more practice with that later. And then the last one is transformation notation for dilations. Here's a transformation notation for a dilation that's an enlargement. Remember, when we enlarge an image, we're taking the pre-image and we're making it bigger. And we're going to enlarge by a scale factor of 3 to 1. 3 to 1 is an enlargement because the first number is bigger than the second. Remember, the first number always comes from the image or the copy, and the second number always comes from the pre-image or the original. And if you want to enlarge by a scale factor of 3 to 1, here's your transformation notation. xy becomes 3 times x, 3 times y. Here's an example of that. If you start off with the original point 4, 3, what's going to happen with that is it's going to be multiplied times, it's going to be multiplied times 3. So 3 times 4, 3 times 3. So you can see that both coordinates are getting multiplied by 3, and so our final answer is going to be at the coordinate 12, 9. So taking 4, 3 and enlarging it by a scale factor of 3 to 1 is going to get you to 12, 9. By the way, again, just like rotation, we are using the COD, or the center of dilation, is the origin. Let's put a little note here on that. Okay, so in the comment, in the notes right here, the center of dilation is the origin. Otherwise, this does not work. And that's the only thing you have to be able to do in this unit, is use the origin as the COD. One more example as we wrap this up. What does a reduction look like? So instead of enlarging, we are going to reduce the pre-image and make it smaller. So let's do a scale factor of 1 to 2. 1 to 2 is a reduction. And here's the example of that. If our scale factor is 1 to 2, we write that as 1 over 2. That means a point on the coordinate grid, both of the values of x and y are going to be cut in half. So here's our example of that. Let's say we pick a point. Our original point was at 4, 6. When we go through our transformation, we're going to end up with 1/2 times 4. Let's write this. I'm afraid I want to show you the example of this. So this is going to be 1/2 times 4 and 1/2 times 6. And when we do that final math, we're going to end up with a new coordinate, which is at 1/2 of 4 is 2 and 1/2 of 6 is 3. So when we reduce by a scale factor of 1 to 2 using the center of dilation as the origin, or the origin as the center of dilation, 4, 6 becomes 2, 3. So there are a bunch of examples on how we use transformation notation. One more thing you guys might want to write, because sometimes students forget what clockwise and counterclockwise is. Clockwise means we are turning the same direction as the hands of a clock. So that is clockwise rotation. And then if you are turning the opposite way of a clock, the clock hands turn, that's counterclockwise. So it's good to have a notation of remembering which way is clockwise rotation, which way is counterclockwise rotation.